Okay. So once you have these two types of forces in your problem, and you don't have forces that are non-conservative, then you can apply what we say conservation of mechanical energy. Okay, and the conservation of mechanical energy will state that it's very simple. It will state that sum of energies at state 1 equals to sum of energies at state 2, and you will demonstrate this in a very simple example. Okay, so here, if you consider a particle attached to a spring, what are the only two forces acting on it? You have the weight and you have the spring force. Okay, so if you choose to apply the work principle of work and energy and not conservation of energy, what do you get? You get that sum of work acting on my system is the work of the weight plus the work of the spring. But we already know that the work of the weight is minus W delta Y if Y is upward, and plus W delta Y if Y is downward. So here, since you choose in your problem the reference, the S-axis downward, then what will be the work of the weight? It will be plus W delta S, okay? So this term represents the work of the weight. And for the work of the spring, it's minus half K S2 square and plus half K S1 square. So when you take the minus inside, it will be plus. So if you try to look at your expression, you can say that I can replace WS2 by what? WS2 is equal to minus the gravitational potential at state 2. Why? Because we said that if you have an axis that is downward, when you have a downward axis, how you write the gravitational potential? You write it as minus WS. Okay? So WS2 is minus VG2 and minus WS1 and minus WS1 is equal to plus Vg1 gravitational potential at state 1. Now also, if you look at the elastic term, the potential term, elastic term, okay, you have that we have minus half K S2 square, and by definition, the elastic potential is plus half K S square. So we can say that this term is, we have here minus V elastic at state 2 and plus V elastic at state 1. From here, we can conclude that for any force which is conservative, the expression of work is V at state 1 minus V at state 2, because it's applied for the work and it's applied for the spring. So instead of doing sum of work as we usually do, we can replace sum of work by V1 minus V2, where V1 represents the total gravitational potential, including gravitational and elastic, and V2 also is the total potential at state 2. Okay, so now we can come up with a new theorem, which is the conservation of mechanical energy, because if you replace in the work and energy theorem, what do you have? In the work and energy theorem, you have that sum of work between 1 and 2, state 1 and 2, is equal to T1 is equal to T2 minus T1. And now we have demonstrated that if all forces are conservative, we can also replace sum of work between 1 and 2 by V1, which is the total potential energy, minus V2. So now if you rearrange your term, you take 1 together and 2 together, you get what is called the conservation of mechanical energy, where T1 plus V1 equals to T2 plus V2. Okay, and this is the formula you are used to use in school. Okay, and of course, if you have a system of particles, all you have to do is, and all forces doing work are conservative. You can say that sum of kinetic energy at state 1 plus sum of kinetic energy plus sum of potential energy at state 1 will be equal to sum of kinetic energy at state 2 plus sum of potential energies at state 2. Okay, so the conservation of energy can be also applied for a system of particles, not only for one particle. So now we still have just this final example to practice on mechanical energy, conservation of mechanical energy. So what we have here, we have a structure is used to test the response of an airplane during a clash. The mass of the plane is 8 megagram, and it's first hosted back until theta equal to 60 degrees, and then the cable AC is released when the plane is at rest. Determine the speed of the plane just before clashing into the ground, corresponding to theta equal to 15 degrees. Also, what is the maximum tension developed in the supporting cable during motion? So here, we have here a simplified figure, which will explain what is happening. So you are testing the clash of an airplane. So what you do, you have first, you have a cable, and the cable is doing with the vertical an angle of 60 degrees. And then you release, yani here, when we cut this, the airplane will be released and it will go down. Okay? Now, what are the forces acting on our airplane? If we represent them, we have the weight of the airplane and we have the tension of the cable. Now, who will tell me the tension of the cable, what will be its work? What will be the work of the tension?
It's 0 because it's perpendicular.
Very good. The tension here is always perpendicular to motion, okay? Because here in this problem, you have circular motion of your airplane. Since the length of the cord is constant, and so the airplane is turning about a fixed axis here. So it's doing a rotation, a circular rotation. And therefore here, a good frame to use is UT-UN. UT is always tangent to the path, and UN is directed towards the center of curvature. So we can say that T is along UN, and since T is always perpendicular to motion, then it will not produce any work. So the only force producing work is the weight. Okay? So now, since the only force producing work is the weight, I can apply the conservation of mechanical energy and say that at state 1, T1 plus V1 equals to T2 plus V2. Okay? Now, since the only force doing work is the weight, then I only have to account for gravitational potential energy. Okay? And to account for gravitational potential energy, I need to choose a reference. You can choose the reference wherever you want. If we choose it here, for example, okay, then the potential energy will be negative at any state. First, at state 1, at A, what is this distance? You have that the angle here is 60 degrees, equal to this one. Okay, and the length of the cord is 20. So you can say that this distance is 20 cosine 16. Okay, 20 cosine 16. So the gravitational potential is negative at this point, equal to, so V at initial point V, gravitational 1, is minus mg times minus mg times 20 cosine 60 times 20 cosine 60. Okay, while at the final state, they said that at the final state the angle becomes equal to 15. So this angle here is 15 degrees. Okay, so to calculate the potential at the final state, you have that the distance here is 20 cosine 15. Okay, so you can write that V at state 2 is minus mg times 20 cosine 15. So now you know the initial and final gravitational potential, and your system is released from rest, so the initial velocity is 0. So the only unknown in your equation, when you write T1 plus V1 equals T2 plus V2, the only unknown will be the final velocity of the airplane, VB. So when you replace in this relation, you can get the final velocity of B. Okay? Now, they asked that for the final position, what will be the value of the tension? Okay, so to calculate the tension now, I should go back to the previous chapter, because when I need a force, I go to the second law of Newton. Okay, and as you can see here, T is along UN. So to find T, I should project along UN direction. So So I will write that sum of forces along UN, okay, sum of Fn equals MAN. And you know that AN is what? It's V square over the radius. So equal to, since we are interested at tension at B, okay, we will apply sum of normal forces at B. So we get mass times VB square over the radius. And the radius of rotation here is the length of the cord, equals to 20 meter. So over 20. Now all we have to do is to project forces on UN. As you can see here, T is along plus UN, while for the work, for the weight, sorry, if you project it, it has a negative projection, and the angle between the weight and the vertical, the weight and the cable, you know that this is the cable, and from given, the cable is doing an angle of 15 degrees with the weight, okay? So you can say that if I project the weight on UN, I will get minus W cosine 50. Okay, so my equation will be the tension at state 2, or the tension at point B, minus W cosine 15 equals to the previous term. Okay, so my only unknown then is what? The tension at B I can calculate. Okay, so next time we continue on these problems, and we will start to do a review for the exam, for the final exam. Any question? Okay, bye.
Thank you.
Welcome.